Richard, are you likely to go over time? We can start 3 minutes early if you'd like.
I don't think so. I hope
Yeah,
not.
people are nodding, so go ahead. Get started when
Okay.
the
Yeah,
next
I
speaker
can.
is Richard Milner.
Thanks, Rupa. It's a pleasure. It's an honor to present to this really beautiful symposium. I've listened to the talk since the beginning. I've really enjoyed it. I was very fortunate in my career to collaborate with Willy and his group, Madison, in utilizing these beautiful polarized internal gas targets to do science. And the target technology, which of course was the principal role of Madison, was, I think, very beautifully described by the talks yesterday by Tom Weitz and Erhard Steffens. So I have decided to concentrate on something I'm working on at the moment, which is visualizing the proton, which is a collaboration between art and science, which I think actually aligns well with Willy's career and legacy. So this is a collaboration. My principal physics colleague is Rolf Ent, who's I think well known from Jefferson Lab. And there are two film producers, Chris Bobel, Joe McMaster at MIT, and a really expert animator from Maine, James LaPlante. So I wanted to start, whoops. Sorry. So I wanted to start with a personal note. I have 3 sons, and 2 of my sons are twins, and we're graduating from high school in 2013. So they applied and were admitted to Wisconsin. Will went to Wisconsin and Sam to Illinois. And so we had a family visit in April 2013 to the Madison area after we went to Urbana. And Baha and Willy kindly showed us around the labs for the physics and the arts class. And these were really wonderful experience. I think you got a sense of it from Pupa's talk yesterday on color and visual. So, we had a really nice dinner. Willy arranged it at a Japanese restaurant, Willy and Gabi and Baha and his wife, and 5 of us, my wife and I, and our 3 sons. So two boys are doing well and they're in physics, and we actually chatted about it earlier this week when I told them about this meeting, and this is something that they remember fondly. So visualizations are a powerful means to describe and understand complicated phenomena in physics. And for example, in freshman physics, typically Newtonian mechanics, we really teach the students how to use free body diagrams, where one isolates a body and determines all the forces and applies Newton's second law or maybe torques. This is really, really important. In our understanding, historically, electricity and magnetism, the role of Michael Faraday, who was probably one of the best experimentalists ever in physics, came up with these ideas of field lines for understanding electricity and magnetism, which were then taken by James Maxwell and formulated in a mathematical way. And we still, even when we learn or work out problems in electricity and magnetism at the level of Jackson, we have complicated mathematics, but the field lines are always, at least I think for an experimentalist, essential in terms of understanding it. And in the 20th century, you've seen in almost every talk has a Feynman diagram. And I think generally they're kind of utilized as cartoons, which work effectively. But of course, we all know that they are prescriptions for very precise calculations in quantum field theory. Now, we live in a time where the standard model has been successfully developed. It explains all laboratory data, doesn't explain all physical phenomena, as we know, but it's an enormous success. We experimentalists, I guess, well, we carry out our experiments in very large scale facilities. I mean, nuclear physics in the United States is a $1 billion endeavor annually, and the machines cost a lot of money. So that's, and of course, this money comes from the generosity of the taxpayer. generally, for the most part. Now, the standard model construct for the strong interaction is a bit unusual because the fundamental particles are not detectable. And the important phenomena that we measure are what we call emergent. They come out of the world of QCD. So the basic kind of premise here is, can we make some progress in visualizing the subatomic world so that a non-expert can begin to appreciate its structure? And when I think of a non-expert, I think of an interested high school student, curious high school young person who's not, that advanced in education. But the point is that you shouldn't have to be at the graduate level doing a PhD in physics before you can appreciate the important elements. And I think it's been said, not sure I believe it completely, that if one cannot explain what you're doing to a non-expert in some fashion, then you actually really don't understand it yourself. So here's some images that I like. I'm not going to explain them or talk about them, but an effective image makes you think about how it was taken. So this is the Earthrise from the moon from Apollo 8. Here's a beautiful image of the sun taken from miles underground using neutrinos. And these kind of images, you have to think about how they were done, understand it, and what they mean. I would say that in terms of the trying to visualize the proton, one of the inspirations for me were the data from Hubble, or the photo images from Hubble. These gorgeous multicolored images of the large-scale structure of the universe, the Crab Nebula. And so one of the key realizations I think we had is highlighted here. This is from the Hubble webpage, where they talk about how they use color. And I highlight the important statement, which is that creating color images out of the original black and white exposures is equal parts art and science. And I think once we realized that or understood it, that helped us find a path forward. So this is just an example of that, where the black and white image is on the left and the colorized image on the right. Now, we're about visualizing the subatomic world. And of course, the first thing one realizes, everything's moving. And because of quantum mechanics, particles move at near light speed. Everything's in continual motion. Particles are created and annihilated, and even the vacuum fluctuates. And this image I show here, I think is an iconic one. It's well known. It's by the lattice gauge theorist Eric Lineweber from 2003. And this is an animation of the gluon fields coming out of his lattice QCD calculation. And I think Frank Wilczek actually showed this in his Nobel Prize talk. So actually, one starting point we had, Ralph and I, was to take this and put a quark in it and try to visualize that. But we really couldn't do it, and we couldn't make much progress. So the point of this slide was that animation is essential to visualize the subatomic world. And so we felt we needed an animator if we were really going to do something new. Okay, just let's look at consider the standard model. So I'm not going to explain all of this, but the standard model has been developed certainly over the last 50, 100 years. Since 1950, I count at least 18 physics Nobel Prizes that go into this. We categorize, it's kind of the periodic table of the fundamental particles. The Greeks talked about atoms as indivisible, but today this is kind of what we think, our physicists would think, subatomic physicists would certainly think as the periodic table, which shows quarks and leptons and the Higgs particle, and of course Einstein gravity, which gave us gravitational waves. So this, as I said, has been tested, and every so often there's a 2 sigma, 3 sigma, 4 sigma deviation from the standard model, and we all get excited. And but so far, I think it's fair to say that it's still standing. So now, if one is thinking about the matter in the visible universe around us, how useful is this? It turns out it's not very useful because these quarks and gluons are not detectable by construct. There's a lot of unstable particles. There are the neutrinos, which have very, very weak interactions. So you're actually left with two particles, an electron and a photon, that are stable. And if you wanted to study in terms of the standard model, this is what nature gives us. Of course, as you've heard, in reality, as nuclear particle physicists, we do experiments all the time with what we call hadrons, which are built from the strong force. So a proton, a deuteron, a nucleus is all a hadron, a pion. And we have a very successful theory of the nucleus and nuclear physics based on this. But how does that relate to the standard model, to the fundamental quarks and gluons? And how, even a basic question like how do you get a proton of a certain mass and a spin a half from QCD is not understood. And in the end, we also study nuclei and their stability. Does QCD play a role in that in some fashion? So I think that the modern thrusts forward are both at the hadronic level, understanding stability, and QCD, understanding how QCD explains the structure of the elements, which are the protons and neutrons. And we hope to build a bridge between this. Okay, so I remind you, a microscope is an object where you can study a leaf or an insect. You scatter light from the sun, and the light is collected in some lenses, directed into the eye of the observer, and then processed. We heard yesterday how non-trivial that processing is, but for this purpose, I'll just assume that it's straightforward. And in the brain of the observer, you know, the structure is analyzed and perceived in that way. So it turns out when we want to study a proton, it's exactly the same technique. Now we have to make a source of photons, which are electrons, and these are large accelerators. The electron comes and interacts with the charges in the proton. Here there are little balls, U, and D, up quarks and down quarks. And the scattered electron is detected in a large spectrometer, and then there are detectors and computers that analyze the data. So the process is very similar, but the scales are very different. So some examples of electron microscopes were HERA, which you've heard about, and the Hermes experiment was in the East Hall. Jefferson Lab has been operating since 1995 in Newport News in Virginia. And in the future, we have an electron ion collider, which we expect to come on at Brookhaven National Laboratory in the early 2030s. Now, just to take a pause at the Hermes experiment, this, of course, was where Willy and Earhart and many groups contributed, leadership, fundamental new implementations of these ideas that had been around to measure the spin structure of the proton and the neutron, and actually, most importantly, develop new techniques, new ways to look at this, which I'll come back to. It turns out that Earhart and I were invited to write our story on this, and we completed a book which is available, but we obviously there's a significant section on the targets, and particular Willy, and Earhart, of course, led that as he was the principal involved. But I do recall some drafts that were sent to Willy, and I don't think he was ever happy with anything he saw. And I remember we have photos, nice portrait photos of principal physicists who were involved in our story, Vernon Hughes, Bob Jaffe. So we had a nice one for Willy, but that was not going to work. So the photo with Willy has him surrounded by Tom Wise and Alexander Naas. And that's a very nice photo. And of course, we were happy to accommodate his wishes. But I think to me, I didn't discuss it with him, but I think it probably indicated how he felt about how he did physics. And a lot of the photos that I see are him with a group of people around him. And certainly that was, now the other thing I just wanted to mention to go back one, for me personally, anyway, this is my opinion. You know, I was sold on internal gas targets to do spin physics very early on. And that was a lot of my career has been focused on that. And when it came time to think about a new machine, it was obvious that the ideal of pure lepton polarized nucleon or nucleus scattering had to be preserved. And it just seems to me that the collider is a natural, you know, evolution of the internal gas targets, in the sense that you don't, I think Steve Vigder's talk this morning on his experiment, charge symmetry breaking, really went into detail on all the corrections that are relevant if you have a lot of extraneous material in the target. And so for me, the collider was the obvious natural way to do that at high energies. And of course, in addition, you get kinematic coverage over a large range. But I just want to make that point. The other point I wanted to make is that we did an experiment in the cooler CE25, which I think was the first polarized target one with polarized helium-3, Jim Sawinski and Jo van den Brand, but certainly Hans Otto, Barbara, Will Jacobs, Steve Pate, many others were part of it. But that actually successfully completing that was actually non-trivial in terms of getting Hermes approved at DAISY, because we had demonstrated that polarized helium-3 was an effective polarized neutron by putting particular kinematic cuts. Otto Heuser's group had done experiments at Triumph where it wasn't so clear. But that was actually a significant, again, activity that happened at the cooler that fed into Hermes. Okay, just reminding you about the properties of the proton. I think these are fundamental building blocks. We have successfully understood the origin of the abundances of the elements, energy generation of star. Basically, a lot of the structure of the universe comes from that. The proton in this standard model, modern perspective, is a highly relativistic system. And I've heard it said, I don't know if it's true, that there are only two really relativistic systems in nature. One's a proton, the other is a black hole. But it's certainly fairly unique in nature in being such a highly relativistic system. And we understand that the proton comes out of QCD from these strong nonlinear forces, which are involved these dense gluon fields. So, you know, going a little deeper now, we scatter from the proton. So this is our Feynman diagram, done in a rigorous way, where a virtual photon is exchanged, and the mass of the photon is given by large Q squared. The real photons have no mass, but this is a virtual photon. And so 1 over Q determines the spatial resolution, and that's what we call the pixel size. Elastic scattering is where the hadronic final state is a proton, so the mass is the same as the initial one. So then you have a very direct relationship between the Q squared and the energy loss by the electron. The really important high energy deep elastic scattering at Q squared greater than 1 and at high elasticity above the resonance region was discovered in the late 60s at Stanford by Friedman, Kendall, and Taylor and their colleagues. And that's where the proton is smashed apart. So you smash the proton and you detect only the scattered electron. And this is the process we call deep elastic scattering. And this is the process that we have animated and which I'll now explain. So again, just a summary. This is a picture. I think this came again from Hermes, where one now starts to see a lot of internal structure dynamics, gluons, quark, antiquark pairs. And so the whole picture of the proton is that now it's largely massless particles. The gluons are massless, and the protons, the up and down quarks of light mass, as Steve explained this morning. But this whole ensemble interacts and has very high, large energies, and results in a proton of mass 938. And so this is energy. This is E equals mc squared, where the energy gives us the mass. What's important for our animation is understanding the relativistic character of the interaction. And this was written down by Bjorkane. And this was the first written exposition of the quark-parton model. It's not a referee publication, it's a Slack pub, which is available. But basically, the electrons are relativistic. The protons can be stationary in the initial state, but they're certainly moving with high velocity in the final state, or in a collider, both can be moving with relativistic speeds. But the point is that one can define quantities, physics quantities that are have a reality independent of the reference frame. These are so-called Lorentz invariants. And the energy in the center of mass is 1, q squared, which I already mentioned, is 1. And then this quantity x, which is defined mathematically here, so-called Bjorkane x. And because of relativity, if one views from a boosted frame, there's a Lorentz contraction. So in other words, the proton will be sandwiched, the target will be sandwiched. And the internal motion of the proton's constituents are slowed down by time dilation. So one can actually capture the instantaneous charge distribution of the proton. And in a particular boosted frame that Bjorkane defined, X is understood as a longitudinal momentum fraction, only in this frame. In general, it cannot be interpreted. And so in this frame, you can identify what are called valence quarks. These are quarks that give the proton its quantum numbers. They are quarks, as Steve defined this morning, they're more like constituent quarks. And then at low X, one has C quarks and also gluons, which arise. These are the virtual particles of QCD. So the valence quarks can radiate gluons. The gluons can produce quark-antiquark pairs. They can be recombination, et cetera, et cetera. So this is directly from Bjorkane's publication, and I think that it's really important in terms of electron scattering to be aware of this. I wanted to remind you about visualization. A camera is a device that captures an image on a desired medium. In the old days, it was photographic film. Now it's usually CCD. And movie cameras are just illusionary. They're just a series of images in time to give the illusion of having captured motion. So there's really just still images, snapshots. That's all we ever have. And two essential elements of a camera are basically the pixel size, which is determined by the focus. I have a picture here of flowers in front of a castle, and you can focus on the flowers or you can focus on the castle. And the other important quantity in visualization is the shutter speed or the exposure time. So all cameras have a door in front that open for a definite amount of time to select light to reach the medium. And so if you want to capture, if you have rapid motion and you have the shutter open for a long time, a long exposure time, slow shutter speed, then the motion's blurred. And if you want to capture rapid motion, then you have to have a short exposure time, rapid shutter speed. So I think Tom Clay kind of talked about this yesterday, but I'm actually hopefully going to show an animation. So again, this is something you all know, but it's to give you the scale. I like the factor of 100,000 brings me from a meter to Reynolds wrap, which is one of the things in our kitchen, which is every day, but you can't make things too much thinner than that around the house. If you go another factor of 100,000, you get to an atom. And then if you go another factor of 100,000, you get to a proton. So James LaPlante made this little video of zooming in. You can recognize Boston or Cambridge. So we end up on top of the MIT Dome. And what we're doing is just showing how, as you zoom in, as you decrease the pixel size, you get to smaller and smaller dimensions. And eventually you end up at a proton. These are supposedly water molecules moving, and got a hydrogen atom, and So then we come to a proton. Okay. So we're almost there, ready to see the animations, but I just wanted to point out that again, the snapshots are where X is the shutter exposure time, and we can have low X where we probe nonlinear dynamics, medium X. This is technical jargon, physics jargon, radiation dominated, and then at high X we would expect to see the three quarks, the valence quarks, and again the shutter speed is shown. So I wanted to go back to physics now and remind you that the cross section for EP, this deep elastic scattering, where you smash a proton apart with a high energy electron, is given by the Mott cross section, which is just the point-like, if the proton had just the charge, times this structure function, we call it F2, which depends on X and Q squared. And this is from the particle data book. This shows you F2 as a function of Q squared in different X bins. And the pink data are from SLAC. So the constancy of the pink data was the Nobel Prize for Friedman, Kendall, and Taylor. And the rise with Q squared at low X came from Hera, from the collider experiments at Hera. And they demonstrate experimentally the role of glue. And from these data, you can determine the gluon distribution. And, you know, as part of that understanding, the theoretical understanding of that, Wilczek, Politzer, and Gross got the Nobel Prize in 2004. So it's kind of interesting where one diagram, if it's flat, it's the Nobel Prize, and if it's rising, it's kind of leading to another Nobel Prize, but very, very profound. And so 1 over Q is pixel size, 1 over X is shutter speed. Of course, there are very sophisticated and rigorous equations that describe all of this, and in particular the QCD evolution equations connect the quark and gluon PDFs. So you can take that F2 now and you can look at it as a function of Q squared. So this is just an animation of the parton density distribution. So this is the up, down, valence. The gluon and C are divided by a factor of 20. They're multiplied by 0.05. So when you get to high Q squared, you see the predominance of the gluons in the C, and the gluons are really dominant at low X. And so one open science question is, we do not expect these distributions to rise indefinitely into the ceiling. At some point, they must turn over, saturate, and that's actually a strong motivation for studying at the electron ion collider, studying nuclei. So now I wanted to show you the animations. And so for about 2 decades, Rolf and I struggled with this. And then in about 2017, some people at MIT, Krishna Rajagopal, Peter Fisher, my department head, kind of led me to the Center for Art, Science, and Technology, which is a center at MIT. And I was introduced to the to the film producers. And so this shows you at low X, 10⁻⁴, roughly, imaging the gluons and what they would look like. And then they gave us some money and then told us go off to find an animator. It took us at least a year and a half to locate James, which the film producers did. So now we're moving to X of 10⁻², and we're seeing more of the evidence of quarks. And then we started work, I think, in the fall of 2019. We actually have had only one meeting where we were all present, because when COVID came, you know, everything was on Zoom. And here now you see to higher X, you see the valence quarks predominating in the 3 different colors. And it's interesting the way the animator made it. There's actually a theoretical question of how these quarks interact and what kind of geometric form they make. There are actually papers that people have seen this and brought it to my attention. So this is Q squared now. We're going from Q squared of 1 to 400. And we have 2 views. We have on the left, the pancake view, which is really all that's been measured. That's pretty much the work that's been done, you know, since the late 60s. On the right, we have a frontal view. If we could see the front of this object, this is what we would see. That's at X of 10⁻⁴. So we'll have 10⁻² coming up, which is where we start to see, there's a quarks. Now, as Q gets large, the spatial resolution gets better. 1/q is a pixel size. So here you start to see hints of maybe the valence structure. And then finally at higher X, it's dominated. And, you know, this is the kind of the parton, the non-relativistic quark model of the proton. And again, the frontal view with all the measurements pretty much have been in the direction of the boost and longitudinal. So clearly, a major new avenue to look at all this would be if you could look in the directions transverse to longitudinal momentum. And indeed, this has been a major focus for several decades. A new class of scattering process was identified. I remind you the DIS process that we just animated is where the protons smashed apart. This new process is a non-violent process where the proton is left intact. And these are called deeply virtual exclusive processes. Here now is just another cut through this showing you the PDF on the left and then the animation on the right for different values of q squared as a function of x. But let's finish this. Okay, so the point is that these deeply virtual processes are really a new avenue that we're exploring. It's actually being done at Jefferson Lab. Actually, 3 of my own graduate students are working in the class collaboration, extracting cross sections. And so there's a large theoretical effort. There's a group called the TMD collaboration, Transverse Momentum Distribution Collaboration. They're just about to release a handbook about 500 pages thick on the momentum distributions. And I should say there's a whole rigorous framework to go with this. I should also say that the Hermes experiment with the targets from Madison and Earhart and others pioneered many of the measurements that of these new processes. Okay, so I think I'm ready to finish. For the first time, we've developed a new animation-based framework. We think it's useful for communication, to understand and explore. We have taken a rather straightforward minimalist approach to the distributions. You can take, you know, calculations or fits to CTEC or lattice QCD or whatever your favorite distribution is, and you can animate that. That's totally possible. We hope that these first generation animations motivate people to do more of this kind of work. We have a kind of an outreach program where we put it on YouTube, and I've never put anything on YouTube before, but as far as I can tell, there's nobody throwing tomatoes at it, and it's generating some interest. We also had a really nice outdoor affair at MIT in April. It was a rather chilly evening. We had 90 people sitting outside for, I think it was 2 hours, basically looking at these animations and discussing it. Krishna Rajagopal was the chair. That's Leela Whitney, who's the director of the center, Ralph Vent, James LaPlante, Chris Bogle, and myself. We had a lot of children there, so it was fun. And the other thing is that the film people, Chris and Joe, are putting together a documentary on the making of this, and this will be premiered in October at the Cambridge Science Festival. And we're planning further animations and videos. We actually would like to introduce spin, and we actually would like to make videos of the nucleon structure of nuclei. We think this could be useful. I'll stop. Thank you.
Thank you very much, Richard, for an animated talk. I look forward to questions.
Hi, Richard, Steve. So it's very cute. It's sort of a Google Earth picture of the proton. I had a specific question about an animation choice. I noticed when you got to large X, that what you might think of as constituent quarks were lumpy. Was that meant intentionally to indicate some structure of the constituent quarks, or was it just an animator's decision? Or
Well, there wasn't a lot of discussion or thought went into it. Let me put it that way. So I don't want to say the animator did it alone, because anything he did we checked. But I guess I think there's some sense of that in it. But I wouldn't read too much into it. I guess it was also like what I said, how they interact, this Y-shaped interaction. It turns out some theorists have calculated this, and there are different ways that the three, I guess, constituent quarks can interact or be arranged geometrically. And apparently this is preferred by some group of theorists. But no, there's nothing profound. I mean, we did, at this level, I think one could imagine taking more care and putting more thought and having long discussions of how to do it. But we kind of went for the simplest thing we could make at this point.
Krishna Kumar.
Hey, Richard, it's KK.
Hey, Krishna.
So I was thinking about one thing which always bothered me about when we try to talk to high school students, et cetera, is you talked about these 3 factors of 10 to the 5. And I'm wondering if there's some way, or did you guys think about, I liked your animations for the first, the X dimension. And I'm looking forward to seeing what you guys come up with for the transverse visualization. But you've thought about whether you could keep reminding people about those 3, 5 orders of magnitude you've gone down, so that as you're looking at this, you don't imagine something really large and spherical, but you keep reminding people that you've gone down these 3, 5 orders of magnitude, and that these are ridiculously tiny things to begin with. So I feel like we have to keep reminding people about where you are in that dimension.
No, it's a really good point you make, Krishna. I mean, I think the world that we do our research in is so different from what people are used to, that I would say any way, I'm not saying what we've done is the most effective. I think any way that one can find to get it across. And I mean, the whole thing is kind of, when you think about it, is amazing that what we can do at such a tiny scale, and what we can learn, and what has been learned is actually pretty astounding if you think about it. So yeah, no, I as I said, we made these animations, and it certainly wasn't our full-time activity or anything close, but I would encourage colleagues or anybody who has good ideas to pursue them, and I think there's a real interest and an appetite, not for everybody. It's I don't think you're going to make a lot of money out of it, but I think you can excite certainly young people who would be interested, might become really interested, and follow it as a career. I mean, that's kind of where I'm at.